In this module, we will learn to evaluate the relative oxidation states of various organic molecules, such as if we have an alcohol functional group compared to a ketone group, which of those would we describe as being more oxidized versus the other way to look at it is which would we describe as being more reduced. This terminology and this concept is important because oxidation reactions are very, very important biologically. They are involved in such processes as the metabolism of ethanol, the metabolism of drug molecules, and the metabolism of a variety of other food components. And so we need to be able to effectively recognize when we're comparing structures which one is more oxidized and which one is more reduced. That will set the stage for later segments where we will look at oxidation reactions in more detail. But first things first, we need to be able to evaluate two molecules side by side and say which is more oxidized and which is more reduced. Let's go ahead and take a closer look at that. When we talk about oxidation in general, we will define oxidation as an increase in the number of bonds between carbon and an electronegative atom, such as most commonly oxygen, hence the name oxidation. So oxidation corresponds to an increase in the number of bonds between carbon and oxygen. That is going to correspond to a decrease in the number of bonds between carbon and hydrogen, because the way that we increase the number of bonds between carbon and oxygen, we have to get rid of carbon-hydrogen bonds. Otherwise, we would end up going over the octet rule, and we can never go over the octet rule. And so if we were to look at two substances side by side, say we had this aldehyde molecule relative to an alcohol molecule. So in both cases, we have a 2-carbon aldehyde and a 2-carbon alcohol. We would describe the aldehyde as being the more oxidized molecule because the aldehyde has 2 carbon-oxygen bonds versus the alcohol only has 1 carbon-oxygen bond. How did we count that? Well, we counted that as we look at this carbon-oxygen double bond there. Each of the 2 bonds here and here count, and so we have a grand total of 2 carbon-oxygen bonds in this more oxidized molecule, whereas in the less oxidized molecule, if we take a close look at our carbon-oxygen bond here, that's just a carbon-oxygen single bond, and therefore being a carbon-oxygen single bond, that's only going to count as 1 carbon-oxygen bond there. And so we would say that the structure on the left is the more oxidized molecule. We could also, in describing the one on the right, we could say it's less oxidized, or we could say that it is more reduced, because the opposite of oxidation is reduction. Reduction, in contrast to oxidation, reduction reactions also are common biologically, and what reduction reactions do is they will result in a decrease in the number of bonds between carbon and an electronegative atom such as oxygen. And we're using oxygen here as what I'm listing rather than more generally listing electronegative atoms, because carbon-oxygen bonds are what are going to be most relevant biologically, particularly for purposes of the applications that we'll be looking at in later videos here. And when we decrease the number of bonds between carbon and oxygen to keep an octet on the carbon atom, which is critical, we have to increase the number of bonds between carbon and hydrogen during reduction reactions. And so the outcome of a reduction reaction would be that when you compare the starting material to the product, you would note that the number of bonds between carbon and oxygen have decreased. So for example, if we were classifying this reaction as an oxidation reaction or a reduction reaction, so we're going to classify it as oxidation or reduction, ox or red for short. Looking at this, we start with 3 carbon-oxygen bonds because we have 2 carbon-oxygen bonds here, 1, 2, and then a third one running over to here, so that's 3 in total, versus over here we only have 1 CO bond, that's from here to here, and so our number of CO bonds has decreased, and the rule is if the number of CO bonds decreases, that would correspond to a reduction process or a reduction reaction. So therefore, we would classify this particular reaction as a reduction reaction. On the other hand, so going in this direction, it's reduction. If we were going the other way with this process, starting on the right side and moving toward the left, so right side is the reactant, left side is the product as we follow the bottom arrow here, we would refer to that process, following the arrow that runs from right to left, as oxidation, because in going from right to left, we are increasing the number of carbon-oxygen bonds. And so we can classify a variety of reactions as oxidation reactions or reduction reactions, completely contingent upon whether we're increasing or decreasing the number of bonds between carbon and oxygen. Let's do an example problem here where we are asked to classify or rank the following structures in order from least oxidized to most oxidized. So rank in order from least, and we'll put that in as number 1, to most oxidized. And we'll put that in as number 4. Let's go ahead and get started on this. We'll draw in some kind of crazy functional groups here that may go beyond ones that you have specifically studied or looked at so far in order to understand here what we are working with. All right, so taking a look at our structures here, and we need a 4th structure in there as well. We will rank these according to most oxidized as number 4, least oxidized as number 1. So counting the number of carbon-oxygen bonds in each case is going to allow us to determine what is most oxidized, because most oxidized is going to correspond to the largest number of carbon-oxygen bonds. Least oxidized is going to be the lowest number of carbon-oxygen bonds. Counting that up or highlighting that through here, in the case of the structure on the left, we have 2 CO bonds in place. Coming to the structure that is second in line here, we have 2 carbon-oxygen bonds here plus 2 over here makes 4 plus 5 and 6. So that's going to have a whopping total of 6 carbon-oxygen bonds. That is quite highly oxidized. Coming over to the next one in line, we have 2 carbon-oxygen bonds here from this carbonyl, 2 carbon-oxygen bonds here from this carbonyl. And so that's going to be a grand total of 4 carbon-oxygen bonds. And then coming over here, we have a total of no carbon-oxygen bonds whatsoever. Ranking these based on the number of carbon-oxygen bonds will allow us to plug in that our least oxidized molecule that has the fewest number of carbon-oxygen bonds is going to be the structure on the far right. So we'll put that in as number 1. Most oxidized is going to be number 4. That would be the one here that has 6 carbon-oxygen bonds. And then in the middle, we have 2 carbon-oxygen bonds here versus 4 here. So that will allow us to rank that as number 2 and as number 3 in our lineup here of ranking from least oxidized to most oxidized. And this is one of the key skills in evaluating structures and comparing them and determining what reaction has happened or predicting what types of reactions will happen with them is looking at their oxidation state. In the next videos, we will apply this information toward looking at oxidation reactions, including applications of oxidation reactions in such things as alcohol metabolism, where we'll answer questions such as how is ethanol metabolized by the body, and we'll also get into the question of why is methanol, which was previously used as antifreeze before it was deemed to be too toxic, is very, very often fatal and certainly very, very toxic compared to ethanol.